Okay, so where the last video ended, we were just finding the velocity that the boulder reached when it got to the bottom of the hill. So it was 16.92 meters per second. That's the final velocity at the bottom of the hill, but it becomes the initial velocity of the boulder as it smucks into the shack for our momentum piece. So for our momentum piece, it's going to be m of the boulder, v of the boulder initial, plus m of the shack, v of the shack initial. It's going to equal m of the boulder plus m of the shack, v final. The shack's not moving initially, and we want the final velocity of the shack and boulder together, so divide both sides by the two masses. So m of the boulder, v of the boulder initial, divided by m of the shack plus m of the boulder. So V final equals, the boulder was 55.6 kilograms. The velocity we found was 16.92 meters per second. And the two masses, 55.6 kilograms plus 204 kilograms. V final equals 3.625 meters per second. So this is the velocity with which the boulder and the shack, after the collision, begin to slide across the ice, so that it becomes our initial velocity for the last step, which is energy. And I need to turn the page because I definitely can't get it in back there. Okay, so the third part then is 1/2 mv initial squared plus mgh initial plus 1/2 kx initial squared equals 1/2 mv final squared, mgh final, 1/2 kx final squared plus E lost. Okay, so initially as it starts to slide across the ice, it has a speed, but it doesn't have a height. There is no spring. It slides until it stops. Still no height, still no spring, but there is an E lost. Friction is causing it to lose speed. Remember, E lost is equal to work done by friction, and work done is F delta D cos theta. This is friction, so we put an FFR in here, and it's acting opposite direction of motion, so there would really be a negative there. It's a level surface, so friction is really mu Fn, delta D, and the angle is going to be 180. So the 180 and the negative are going to cancel each other out, and this will really be 1/2 mv initial squared is equal to mu Fn on a level surface is just mg. If it had slid up a bank, it would have to be like mg cos theta for the component, but it isn't. This m initially is the mass of the shack and the boulder together, and so is the m finally, so they cancel. All right, and we're looking for delta D, so divide both sides by mu g. So delta D is equal to 1/2 vi squared divided by mu g. So 1/2, and the v is the last v we found, 3.625 meters per second. Don't forget to square it. Divided by the mu they told us in the question was 0.392. And g, of course, is 9.81 meters per second squared. So assuming you have remembered to square it, you should get 1.709 meters. Okay? The final answer. All right, I also asked you to do number 5 and 6 on this sheet, conservation of momentum and energy. So number 5 is a dart that you're throwing at a target. So it's a pendulum one again. Okay, so we have a dart, and we're throwing it at a target. And after the collision, of course, the dart and the target stick together, and they swing up to some height. Okay, so I'm going to do this. And so it tells us the mass of the dart is 6.5 grams. And the mass of the block, oh, it's a block, sorry, I drew it as a circle. The mass of the, I'll just call it target, is 2.2 kilograms, which hangs on an 84 centimeter long string. So this is 0.84 meters. Swing to a maximum angle of 25 degrees. So this one is going to be exactly like the baseball one that we just did. You're going to draw your line over here. You're going to find this length, y, and then you're going to take it away from the 0.84 to find your height. Okay, so first step, it's adjacent side, so cosine of 25 is equal to y over 0.84. So y is equal to 0.84 meters times the cos of 25, which is 0.7613 meters. And then we have to take, to get our HF, we take that away from 0.84. So 0.84 meters minus the 0.7613 meters gives us a final height that the pendulum reaches to be 0.0787 meters. And so that becomes our height in our energy section of the question. Okay, so now we do energy. 1/2 mv initial squared plus mgh initial 1/2 kx initial squared equals 1/2 mv final squared mgh final 1/2 kx final squared plus E lost. So initially, as it goes to swing up, it has a speed but no height and no spring. When it reaches its maximum height, no speed but a height, no spring. So we have 1/2 mv initial squared equals mgh final. In this section, as it swings up, it's the mass of the pendulum and the dart. And when it gets to the top, it's the pendulum and the dart as well. So the m's cancel. You're looking for your VI. So 2GHF, so 2 times 9.81 meters per second squared times that 0.0787. I don't know where the edge of my paper is. Meters. So VI squared, oops, no, I'm just going to do it in one step. VI becomes 1.243 meters per second. Okay, and this then becomes the V final of the momentum piece when the dart hits the block. Okay, so for momentum, mass of the dart, velocity of the dart initial, mass of the target, velocity of the target initial equals mass of the dart plus mass of the target, V final. And this is my V final. Target's not moving, we're looking for initial velocity of the dart. So m of the dart, m of the target, V final over m of the dart. Okay, you're going to have to change that m of the dart to kilograms because it's in grams and the block is in kilograms. So 6.5 will be 0.0065 kilograms plus 2.2 kilograms times our 1.243 meters per second divided by, and this is just mass of the dart, so 0.0065 kilograms. And you're going to get a big number here. That's why you shouldn't stand in front of a dart. You get 421.8 meters per second. I'm thinking this dart must have been fired from a gun. If someone fired it by hand, sign them up to your teams. Okay, so that's number 5. Number 6, we're going to run out of time, and I'm going to have to go to one more video for it because I only have 10 seconds left. An 850-gram block of wood with Velcro on one end is slid across the floor towards the second block, 1.2 kilograms.